So the next thing that we need to look at is an application of continuity of functions, and this is called the intermediate value theorem. Before watching this video, I hope you checked out that magic trick through Desmos to kind of get a sense of what this intermediate value theorem is about. This is all about guaranteeing those particular y values. Let me draw a picture and I'll write out the theorem at the same time. Let's say I have some x value a, some other x value b, and I have a y value over here, another y value over there. Guess I should probably label those y values. Let's see. I'm going to call this y value f of a, and this y value over here f of b. Here's what our theorem says. First of all, a very important requirement of this intermediate value theorem is the fact that this function is continuous, and hopefully you also saw that in the Desmos activity. If the function is not continuous, we can't make any guarantees. If f of x is a continuous function, on the interval from a to b, then f of x must equal all the y values from f of a up to f of b. I'm going to say f of x must equal all y values between f of a and f of b. Now, the way this is usually going to work is I'm not necessarily going to be looking for a range. I'm going to be looking for a particular y value, and I'm going to want you to guarantee that there is some particular y value. Let me pick some random y value. I'm going to call that k. Can you guarantee that there is some x value that has a y value of k? Well, sure, by our intermediate value theorem. Looks like that x value is over here. I'm going to call this x value c. To conclude this, and I realize this is going to seem a little wordy, just stick with me on this. Specifically, there exists some x value, c, such that f of c equals k. For any k value between f of a and f of b. Take a moment, pause that video, get all those words down, and then we'll see how to apply this. This is just what you saw in that magic trick, just written out a little more formally. Pause the video and make sure you finish copying that down. I would like to show that the function f of x, which equals x cubed plus 2x minus 1, has a 0 on the interval between x equals 0 and x equals 1. This is going to be an application of this intermediate value theorem. I'm trying to guarantee that somewhere this function is going to have a y value of 0. Well, the first thing I need to do is figure out f of 0 and f of 1. I need to know those y values at the endpoints. F of 0 is going to equal 0 cubed plus 2 times 0 minus 1, and f of 1 is going to equal 1 cubed plus 2 times 1 minus 1. That's a negative 1 over there. That's a 2 over there. I know very, very little about what this function looks like. But I know that it has a point at 0, negative 1, and a point at 1, comma 2. Since that function is continuous, because I know all polynomials are continuous, wouldn't it have to cross the x-axis? This is an application of the intermediate value theorem, and there's a specific way we're going to write this out. First of all, I know that my function's continuous, so I'm going to actually state that. Since f of x is continuous, I guess I'll say continuous everywhere, although we only really care about between 0 and 1. And since f of 0 equals negative 1, and f of 1 equals 2, by the intermediate value theorem, f of x must equal all y values between negative 1 and 2. Since f of x is continuous everywhere, and f of 0 is negative 1, and f of 1 is 2, by the intermediate value theorem, f of x must equal all y values between negative 1 and 2. Which y value was I trying to guarantee? 0. 0 is between negative 1 and 2, so it's going to work. So my conclusion is going to be specifically, there must exist a c value such that f of c equals 0. Specifically, there's a particular x value that I'm going to call c, such that the y value there is 0. This is the language we're going to need to write these things out. There are several ideas that must be included here. You must explicitly mention that the function's continuous. Well, and I think before you do that, you've got to make sure your function actually is continuous. No zeros in denominators, no jumps from one piece of a piecewise function to another, at least over the interval that we care about. In this case, it was 0 to 1. You need to find the y values at the endpoints. I found f of 0 and f of 1. You need to state the theorem you're using. I'm going to state by the intermediate value theorem. No abbreviations. IVT doesn't really mean anything. Write out the theorem, write out the name of the theorem in full. Because of that, we know the range of y values, so I'm going to state that it has to equal all the y values between negative 1 and 2, and then I'm going to deal with my specific y value that I'm guaranteeing. I'm guaranteeing there's an x value, c, such that f of c equals 0. Let me give you another one that I'd like you to try to write out, really just using this as a template. I really would take this exact same language over here and just fill in different numbers for the different functions. Let's try this one. For f of x equals x squared minus 4x minus 6 on the closed interval from 3 to 6, show that there exists a c such that f of c equals negative 1. I want you to prove to me that somewhere this function is going to equal negative 1. Then I'm actually going to add another piece into this. Then find it. Find where that happens. This is a little different. This actually has nothing to do with calculus. Don't worry about that for right now. I'd like to see if you can pause the video and write out your paragraph trying to guarantee, if possible, that somewhere that function must equal negative 1. Yeah, that's looking good. My y values have to be between negative 9 and 6, And I'm looking for a y value of 1, so here we go. Since f of x is continuous and since 3 equals negative 9 and f of 6 equals 6 by the intermediate value theorem, f of x must equal all y values between negative 9 and 6. The one I cared about was negative 1, so I'm going to say specifically there exists a c such that f of c equals negative 1. And this is the argument to prove that, yes, my function has to have a y value of negative 1 somewhere. I then asked you to find it. Well, to find it, all we need to do is set the function equal to negative 1. And we're going to solve. 0 equals x squared minus 4x minus 5. I can factor that thing into x minus 5x plus 1. So I'm going to get x equals 5 and negative 1. However, I don't actually care about both of them. It's nice that there were 2 places, but didn't have to be 2 places. I just knew that 1 place was going to happen. I was just looking for x values, though, between 3 and 6. I found 2 of them. This is the one that my intermediate value theorem guarantees. The negative 1 is just an extra little bonus. The intermediate value theorem often shows up as part of a free response question on the AP exam. And usually it's not just with formulas and stuff, it's usually in a little bit more of a context. So I would like to take a look at one more thing. Hopefully you printed out a copy of the 2006 AP Calculus AP Free Response question number 6. I'd like to see if you can pause the video, read this problem, and see what you can do. Well, let's see. I'm trying to prove that somewhere the velocity is going to be negative 5. Well, because my velocity function is continuous. Actually, first of all, that bottom line of acceleration things, I don't care about that at all. I'm just going to cross that out. I'm going to say, since v of t is continuous, I know it was continuous because it said it right over there, and v of 0 equals negative 20, and v of 60 equals 10, by the intermediate value theorem, the pen's drawing out, so let me try another one. By the intermediate value theorem, v of t must equal, this one's not much better, must equal all y values, or how about just all values? Yes, they're really the values here. All values between negative 20 and 10. Specifically, there is a time c such that v of c equals 0. One other thing I want to mention. Can we guarantee that somewhere the velocity is going to be 5? Sure, 5 is between negative 20 and 10. Can we guarantee that somewhere the velocity is going to be negative 15? Sure, negative 15 is between negative 20 and 10. Can we guarantee that somewhere the velocity is going to be negative 25? Even though negative 25 is not between negative 20 and 10, what if I just look at this interval over here? Between time 0 and time 15, I know my velocity has to take on all values between negative 20 and negative 30, and negative 25 is within there. So I can prove that between time 0 and time 15, somewhere my velocity is negative 25. So somewhere in this interval, my velocity is negative 25. Somewhere in the entire interval, specifically over here, my velocity has to be negative 25. Sometimes you're going to have to look at a smaller sub-interval to reach your conclusion about a particular value guaranteed.